Yeah, good morning. The subject for today's talk is about multi-item auctions. And this really is a fairly well-known subject. It's the classical auction by Bayesian to maximize revenue is for one item and n bidder, and it's a very well solved problem. But when there are k items, then the problem becomes much more difficult, and so there's a lot of work done on this subject in recent years. And generally, the goals are first to try to design simple mechanisms that can achieve optimal revenue or close approximate optimal revenue, and also hopefully we can answer some of the structural questions concerning the theory of multi-item auctions. For example, when you have several auctions, is it better to do them simultaneously, combine them together to get more revenue, or is it okay to do them separately? And also the question of what kind of equilibrium concept you use. For example, the two most common ones used are called the dominant strategy equilibrium or the Bayesian equilibrium. So the question is that does it make any difference if you have a different concept of the incentive compatibility? And also the question is that if you are try to sell the items to a community of buyers who are more willing to pay more, can you get more revenue out of it? And today we are going to try to focus on the question of whether the Bayesian equilibrium versus the dominant strategy equilibrium, whether it's strictly better for the Bayesian one, and what the gap is. And there's a lot of work done on this subject, many of them very beautiful and elegant, so I will not have time to go over them. So I just show a example of some of the work that have been done in this area. And so the question we are interested is the dominant strategy incentive compatibility versus the Bayesian incentive compatibility. And we all know that the dominant strategy incentive compatible is a very strong one. It just means that if you use this mechanism, then in any circumstance, the bidders have an incentive to just tell the truth. Now the Bayesian one is more relaxed. It's just saying that the constraint on the mechanism is such that for any particular buyer, stochastically, one has an incentive to just tell the truth. Although in specific circumstances, you may regret that you have told the truth. So, but the question is, does this buy you anything for the Bayesian incentive compatible? And these are I think it's really surprisingly that they are equivalent in the one-item auction case. And also, in Bayesian's work, it not only has this property, but it actually gives you explicit revenue formulas for the revenue. And so now there are two natural questions in order to try to generalize Bayesian's auction result to the multi-item case. The question number one is that if you have more than one items, can BIC mechanisms ever produce more revenue than the dominant strategy mechanisms? And a related question is that in this circumstance, if you have more than one item and more than one buyer, can you obtain explicit revenue expressions for some interesting family of distributions? And in this talk, we are going to give an answer that is yes for both questions. And moreover, we're going to get some insight upon the difference between the dominant strategy and the Bayesian incentive compatibility. And so specifically, we'll get an intuition on why that the Bayesian mechanism can give more revenue than the dominant strategy one. And also, we can see that if sometimes it's possible to get a Bayesian incentive compatible that has more revenue starting from a dominant incentive compatible mechanism. And secondly, that we are going to we'll have some optimal, actually quite simple mechanisms, and they are simple in the sense that they are essentially allocation driven. That you should specify how you allocate them, and then the incentive compatibility will naturally tells you what kind of payment you should derive, and that the allocation method that is used is very close to being the very purely hierarchical allocation schemes. And now, thirdly, by answering such questions, when we get exact revenue formulas, they are valuable to use for benchmarking and interpreting economic concept when you want to do experiment on it. And so the outline of the talk will tell you what the main theorem is and some consequences of the main theorem, and they are quite interesting. And after that, we'll give some intuition how the Bayesian incentive compatible mechanism could yield more revenue than the dominant strategy one. And then we're going to tell you something about the optimality proof of such mechanisms. And in this process, it's going to tell us something more about the nature of the contrast between these two types of mechanisms. And then lastly, we'll give some conclusions. And so let's specifically consider a very simple type of auctions. Let's consider the end bidder just only 2 items. So it's almost as simple as possible. And the distributions, they are all independent IIDs. And so there's exactly one distribution for any bidder and for any item, and they are independent. And furthermore, they are really simple. The support of the IID, there are only 2 values. So it's just there's a low bid, there's a high bid. The low bid is A, and the high bid is B. So B is strictly greater than A. So sometimes we can just think just to normalize it so that A is equal to 1, then B is something greater than 1. And so on this support, there's only one further parameter, namely that this is the probability P, which is between 0 and 1. That's the probability of getting the low valuation. So such a distribution can be specified by a 4-tuple delta. So it specifies the number of bidders. P is the value of the bias, and A is the low bid number, and B is the high bid value. And the main result is that the optimal for this family, the optimal value for the Bayesian incentive case and the dominant strategy case, they are both piece-least linear functions in B. So let's assume, just regard N and P and A as fixed, and just look at it, how the optimal revenue changes as a function of B. Then it's piecewise linear, and they have 3 breakpoints where B is, so you're starting out with B to be very nearly equal to A, and as you go out, then you encounter 3 breakpoints. And between the breakpoints, the function of the optimal revenue, they are just linear functions in B. And interestingly, that these breakpoints, they don't depend on n. They only depend on p, essentially. And so the main theorem is that they are piecewise linear in B with these breakpoints. And interesting to note that if you, oops. So the blue curve is the one that corresponds to just selling the items, the two items separately, each one of them using the optimum method. And then somewhat better than it is the revenue coming from the dominant strategy. And then using the Bayesian strategy, you can get still further higher revenue. And these revenues, they are starting from B equal to A. They started out to be immediately different. And they stay different until they reach the last breakpoint, V3. At that point, so beyond a certain point, then it doesn't matter whether you are selling it each item separately, or the dominant one or the Bayesian one. So that's something that we, I think, probably should expect, because when one item is much larger, when one valuation is much larger than the high valuation, much higher than the low valuation, then it seems to be reasonable that the good thing is just to sell everything according to using the high valuation as a threshold. But it's interesting to note that the Bayesian revenue is strictly bigger than the dominant strategy revenue, except in the case when the high valuation is sufficiently high that actually you don't need to do anything sophisticated. You just sell things using the high valuation as the threshold. So this is an interesting phenomenon. And now well, here's the formula. So these formula are not just piecewise linear. They actually, you can write down the exact expressions, and you can see that these are the truncated expression for three separate pieces of linear functions, and therefore you get the behavior that we mentioned. So this is the quantitative form of the main theorem. So the first corollary of this expression is that BIC is equal to DIC if and only if selling separately is optimal. And if you look at the expression and try to derive this corollary one, it takes some effort. But we are going to give you some informal argument why we should expect that this is K, and it's for a very interesting reason. And the other corollary is that we certainly expect that if you have continuous distributions, and if they are sufficiently concentrated around two particular values, then the discrete case should provide a reasonably good approximation for the continuous case. And it actually turns out to be the case that if you look at the distribution, the uniform distribution over two disjoint intervals, and for example, one of them started out to be twice the value of the high interval, to be twice the value of the low interval, then for as soon as the basic unit A to be reasonably large, then you have a phenomena that for this kind of continuous distributions, BIC is unequal to the DIC case. So that's the statement of the main theorem. And now we are going to go to the second part, namely to give you an idea why the BIC could sometimes bigger than DIC. So here's a simplest example. You have two bidders, you have two items, and the low valuation is 1, and the high valuation is between 2 and 3. And the two valuations are, the low and high, are equally likely. And now I'm going to first describe to you what the optimal mechanisms are for the dominant strategy and for the Bayesian strategy. And the linear function corresponding to the revenue is as shown, and you can see that they are different. For example, if b is equal to 2, then the ratio comes out to give you a value to be the Bayesian value to be bigger than the dominant strategy by exactly 2%. And now here's the description. So basically, the baseline mechanism is the one that you try to sell each item separately at priced at the high valuation, but you do something a little bit different to modify a little bit. That namely that when one of the buyers has both items to be valued at a low value, then we're going to allow the other buyer to buy the two things as a bundle, and they bundle at the price b plus 1. So that's the kind of the natural thing you want to do. And in this case, both the dominant strategy and the Bayesian strategy do the same thing. And what is different is that suppose one buyer has a combination of a low and a high valuation, and it turns out that the other buyer also has exactly the same pattern, one low and one high. Then in the dominant strategy, we can let Alice and Bob, in this case, it's just that each one would get half of the high valuation item. So this is really just selling separately, priced at B. It doesn't do anything special. But for the Bayesian one, you do something more interesting, namely that you allow both the buyers, each one of them will get half a bundle and the price at b plus 1 over 2. And now, correspondingly, you also have to do something special, namely that if one of them has a low and a high, and the other one has two highs, then in this case, the dominant strategy is still doing the same thing. They're selling both items to the high-valued buyer and getting exactly the full value. But for the Bayesian case, you have to give Alice a discount. So you have to allow Alice to accumulate some utility in order to satisfy the needed incentive compatibility constraint. So that's the description of these two different optimal mechanisms. And now, why does the Bayesian case gain extra revenue over the dominant strategy? Well, if you look at the middle row, you can see that this allows the sellers to sell the low-valued item to Alice. So in that sense, it gives you the possibility of charging more. So you get a little bit more revenue. But on the other hand, you lose some utility because you are selling some low-valued item. Then you have you have to give out the concession. And furthermore, you notice that the mechanism MB is not dominant incentive compatible. If you look at it, the honest Alice gets utility of 1/4 in this particular circumstance, and if he pretends to be evaluation of 1B, then it's going to get a utility to be twice as big as it would have. But the MB is still Bayesian incentive compatible because its overall utility does not increase by cheating, because then if Bob has a valuation of low and high, but with the other combination, then actually in that case, the honest Alice will gain back the utility, and therefore you get the Bayesian case. So this is an interesting case. If you look at you might ask, why is it not possible for Bob to try to do the same thing, try to sell the low-valued one? It turns out you cannot. As soon as you try to sell the low-valued one, you're going to lose utility by the constraint of the incentive compatibility. And that actually goes to the heart of the reason of corollary 1, is saying that as soon as you allow that the incentive compatible to gain something, then the Bayesian can gain more. Okay, and so now, so I'm just going just 1 minute. That the optimal proof for DIC is that basically, in order to do better than the baseline case, you have to try to sell some of the low-valued item. But the low-valued item will forces you to get a formula of the change in revenue in terms of the cheap items you send, and depending on what kind of combination that you get, but you will make money. You will get more revenue or less revenue, and this account for why you get different breakpoints. Okay. So in conclusion, we have given explicit formulas for this family of auctions, and there are interesting questions. Is 2% the maximum gap possible? And also seems that BIC not equal to DIC should be quite common. Can one have a general theorem that to that effect? And also having an explicit form for non-trivial auctions is useful. For example, recent result use it in some deep learning of the optimal auction mechanisms, and there are other structural questions like in revenue monotonicity. And now here's a new result. It's saying that even though strict monotonicity is not true, but approximate monotonicity it's valid. So not only for the additive valuation, but actually for any XOS, namely fractionally additive valuation, you can prove that as you get into a richer community, you will get more revenues. Thank you.